So far, we have discussed about the MEMS pressure sensor, right, in the last class, and we have given the basic introductions of the MEMS accelerometer. Okay, so let us discuss the MEMS accelerometer in details in today's class. Okay, so as we have already told the basic principle of the MEMS accelerometer, so that is nothing but a mass spring damper system. Fine. So as you can see from this particular model, and in last class we have told that this second order differential equations or the transfer functions we can write for this model. Fine, and where the resonant frequency and the basically that undamped natural frequency, damping ratio, these are the important features or the parameters, right? Now that accelerometer, so that is also one type of sensor, and what is its job? Its input is the acceleration, right? So when it will be subjected to some acceleration, then it will give the corresponding output, and obviously our preferable output in will be in voltage or electrical output form, right? Now in case of MEMS pressure sensor, what we have seen that among different type of mechanisms, mainly we have discussed about the piezoresistive type pressure sensor and capacitive type pressure sensor, right? Similarly for accelerometer also we will be focusing on these two types, that is the piezoresistive based accelerometer and the capacitive based accelerometer, right? And the technology which will be used for developing or fabrication of this device, that will be the micromachining technology. Okay, so here just for a representative purpose, here we have shown the piezoresistive accelerometer, and this is the capacitive type accelerometer. So just the schematic diagram we have shown here, and further details we will be discussing in the subsequent slide onwards, right? Now already we have told in last class about the basic structure, that is this is simply a mass spring damper system, and the working principle also we have told that this particular structure, so basically this is the external frame, right, and this is the actual device. So here this is the proof mass, and these are the four springs you can think of, right? Similarly here also this is the proof mass, and these are the four springs in four sides, and here couple of interdigitated beams are there. Fine, and this whole things is kept with respect to a reference frame. Fine. Now when the whole reference frame, that as I told that you can think of as the complete packaged thing, and when you will put that package in the platform where the acceleration is applied, so then there will be movement or displacement in the reference frame itself. And since the mass spring system is again kept within the reference frame, so obviously so there will be relative displacement between this reference frame and this mass, right? And based on that relative displacement, the that relative displacement, that will be actually converted into the corresponding electrical output. So from that output we can tell about that what is my input acceleration applied. Fine. So that is the basic theory. Now since we are talking about the that MEMS based sensors, so obviously the piezoresistive, capacitive, whatever be the types, so typically we can go for this bulk micromachining or surface micromachining technology to fabricate this type of accelerometer device. And also we can have some mixed process which will combine both the bulk and surface micromachining together, right? So this is the overview of the that MEMS accelerometer system. Fine. Now this is mostly the sensor part we are focusing, and afterwards once we understood the sensor, then we will go for the this circuit part or the corresponding ASIC, what we call that part as well. Fine. So is it okay, the basic ideology or the basic principle? Fine. Now just I want to point out that although we will be discussing mainly the piezoresistive and capacitive, but there are lot of other types of accelerometer as well, right? Like resonant type, some tunneling current type, etc. Fine. But just for that get some overviews of the things, just we are focusing on these two types, that is the piezoresistive and the capacitive. Okay, is it okay? Okay. Now in these slides we are going to discuss about that details or that comprehensive analysis of this piezoresistive type accelerometer. Fine. So as you can see here, the first line is written as this piezoresistive accelerometer is the fast micro-machined and fast commercialized micro accelerometer, right? So this piezoresistive accelerometer is the first, that both in terms of micro-machining technology as well as the commercialization's point of view. Fine. Now piezoresistive accelerometer, the working principle is similar to our piezoresistive pressure sensor. That means there will be some moving element. So in case of our pressure sensor, what was the moving element? That was the diaphragm, right? And on the diaphragm we have mounted the piezoresistors. So when the diaphragm was moving, those piezoresistors were sensing the stress or strain, and accordingly their resistance were changing, which we were converting it into the electrical output with the help of the Wheatstone bridge circuit. So similarly, that type of principle will be exploited for this piezoresistive accelerometer development as well. Fine. So the most simplest piezoresistive accelerometer you can think of as a simple cantilever beam. A simple cantilever beam where in that free side you have the proof mass and another side will be the anchored region. Fine. And towards the anchored region or the that fixed substrate we can deposit the piezoresistor, and when that cantilever beam with the mass that will be subjected to the acceleration, it will vibrate, and accordingly the piezoresistance will change, which we can detect with the bridge circuit. Fine. So that is the simplest one. But generally the types or the designs which are preferable for this type of particular piezoresistive accelerometer, so that is this type of design. So that's why we have chosen this particular configuration to design, to analyze details of this piezoresistive accelerometer, right? So what we can see, what it includes. So this external blue portion, rectangular blue portion, is the reference frame or supporting frame, and in the middle this block, what you can find, that square block, so that you can think of as the proof mass, and these four springs, these are in the two sides and these are another two, these four are that springs or the flexors, right? So essentially you can understand that this equivalent model will be a simply mass spring damper system. So where one outer reference frame is there, which is this one as the outer reference frame, and inside we have this one is the mass, and these are the four springs, and their damping force will be also there because of the air damping. Fine. So that's why this will be the equivalent model of the mass spring damper system, where the equations you can see A equals to kx by m. Where from we are getting this? Because if you see this equation, that is nothing but m into A equals to k into x. So that means at steady state, m means the mass of the device and A is the applied acceleration. Fine. So m into A means the total applied force, and that will be balanced by the k into x. So k is the spring constant, x is the displacement of the mass, so k into x, that is the spring distribution force, and m into A, that will be my applied force, because if the acceleration applied to the device is A, so then the force experience will be m into A. And at steady state, if we don't consider this damping case, so then simply this m into A, that inertial force, that will be counterbalanced by the spring force. So that's why ma equals to k into x, right? Where A equals to nothing but k into x by m. So where for a particular design, k and m, these are known to the designer, right? So only A is the unknown, because that unknown acceleration we want to measure. So how we can measure? We will measure this x, and by measuring this x, so basically that x will be generated because of the applied acceleration, x will be generated, and that x we will be measuring either in terms of the resistance change or capacitance change. Fine. And then finally it will be converted into the voltage. So from that voltage, finally that voltage will be calibrated in terms of the applied acceleration. So that is the basic working principle, right? Now let us look at this particular design. So what it consists of? It consists of a proof mass, as we said, in the middle portion, suspended by four thin flexors or beams or springs basically, right, which are fixed at the outer supporting frame, right, because it has to get some sort of support, right, and these are the supporting frames. Okay, now the frame is fixed to the system whose acceleration is to be measured. That means this overall system including the frame, that where we will mount it, the platform for which we want to measure the vibration or the acceleration, right. Now when that particular platform or that systems will vibrate, so accordingly this frame will be also having some sort of movement, or it will experience the acceleration, and the frame will move according to that. And since the mass spring damper system is inside this frame, that means attached to the frame, so this particular displacement will be transferred to the mass spring damper system as well, and obviously there will be relative displacement between the proof mass and this reference frame. And because of that relative displacement, that means this proof mass will be moving, and when it will be moving, that means the spring will be experiencing some sort of stress or strain, basically tensile or compressive force. And because of that, if we deposit some sort of piezoresistors across this these beams or these flexors, so then we can have some sort of resistance change in those piezoresistors which are deposited on these flexors or the springs, right. So then suppose if we use 4 piezoresistors on these 4 springs, or maybe 8 piezoresistors to increase the sensitivity further, so then those piezoresistors will be depending on the applied acceleration directions. Either some of the resistors will be experiencing tensile force, some will be compressive force. Accordingly, some will show the increase in resistance, some will show the decrease in resistance, and that resistance configurations we can connect it to the Wheatstone bridge circuit to convert the delta R into the delta V, right. And in that way, that output voltage will be calibrated in terms of the applied acceleration. So this is the basic working principle of the piezoresistive type accelerometer, and this particular design is widely used. So that's why we are describing this particular type of piezoresistive accelerometer sensor. Okay, is it okay? The basic idea or this working principle or the design aspects of the piezoresistive accelerometer. Okay, so if you have any doubts, please feel free to ask me or get it clarified by either online or offline mode. Okay, fine. So if it is okay, so then we will go for the next, where we have just shown the design and analysis details of this piezoresistive accelerometer, right. So what we can see, that this particular figure already we have shown that this, suppose this square is the proof mass, and these are the 4 springs or the flexors, fine, and this is the outer reference frame or the supporting frame. Now what we have done here, you can see total in each springs we have deposited 2 piezoresistor. One is towards this frame side, another is towards the mass side. Here one, that red correspond to the piezoresistor, here one piezoresistor, here another piezoresistor. Similarly in this spring also, here you can see one red dot, that is one piezoresistor, here another piezoresistor. Similarly for here also 2, here also 2. So total 4 into 2, 8 piezoresistors we have placed here, right. And if we just zoom that portion, so here this particular zoomed portion has been shown over here, where this is my piezoresistance, you can see, right. So this is that straight line, and in the both sides we have some bond pads type of thing to take the electrical connection. So this is the piezoresistor deposited in both the towards the mass side as well as the frame side, fine. Now suppose if we want to use this as an accelerometer, so here we have shown one particular simulated diagram. So simulated diagram, you remember we told that we essentially before doing the actual fabrication process, we need to that analyze it or simulate it using some sort of simulation software, and some of the simulation software names also have mentioned, like Coventorware, Console, etc. Fine. So now if you just see this diagram, so suppose this is your that external frame, and inside we have this proof mass and 4 springs. Now if suppose some particular force is applied from the vertical direction, so then what will happen, this particular mass spring systems will be deflected downwards, Okay, now when it will be deflected downwards, then the springs, total 4 springs what we have, those springs will be feeling obviously some sort of stress along its directions or the axis. Now what we have done, towards the frame side we have put one piezoresistor in each spring and another piezoresistor is towards the mass side, right? So we will show in the next slide that because of this particular if this some vertical directions force we apply, and because of that force, if you that divide that force by the mass, so that F by m, that will give you the acceleration, right? Or you can think of in other way as well, that some acceleration is applied and that acceleration will be multiplied by the mass, and that will be the effective force m into a, which will be applied on the proof mass, right? So that one, and in each as we told, in each spring or the flexors we have two piezoresistors, one is towards the mass side, another is towards the frame side. Fine. Now you look at that the sensing mechanism is the piezoresistivity, and as we said, each flexor contains two diffused piezoresistors, and placement of resistors at maximum stress region, we have to put it one near the frame, another near the proof mass end, as already we have discussed. Now resistance value changes due to the piezoresistive effect in silicon. Fine. Now resistance values of, so total how many piezoresistors we have? 4 into 2, 8 piezoresistors, right? Now if some vertical direction force is applied, so then out of those 8 piezoresistors, 4 piezoresistors will show the increase in resistance, whereas another 4 will show the decrease in resistance, right? So accordingly what we can do, total 8 resistors we can connect it into Wheatstone bridge configuration, and then so that means Wheatstone bridge is having how many arms? 4 arms, right? So each arms we will be putting 2 resistors, fine. So 4 into 2 equals to 8, and obviously as you know, to have the maximum output or sensitivity, the diagonal, 2 diagonals should be having increase in resistance, another 2 diagonal will be decrease in resistance. So in that configurations, total 4 resistors which will be showing increase in resistance, they will be placed diagonally into each arm, and in another diagonal arm we will be putting the other 4 resistors which will be showing decrease in resistance. Fine. And accordingly when the force or the accelerations will be applied, so because of that the resistance change will happen, and that resistance change will be converted into Wheatstone bridge, that means the voltage output using the bridge circuit, and finally that bridge output voltage will be calibrated in terms of the input acceleration, right? So this is the further details, and the here just the we try to show that this is the actual design, and further working principle illustrations has been done, and also the how the simulation characteristic looks like using the simulation tools. If we simulate it, it will give you the stress distribution, strain distribution, resistance change, so those factors it can give you. So after doing the simulation, you can understand that whether your the design dimensions what you have chosen, right? What should be the dimension of the mass, what should be the dimension of the springs, so whether they are fine or not to achieve the particular target specifications. If they are not satisfied, so then again we have to change the dimension, again resimulate it, and then we have to finalize at our targeted values, right? Is it okay? Yeah. So next let us see. So here we have shown the Wheatstone bridge configuration, right? So as we said that when this particular example, so when suppose this is the that piezoresistive accelerometer, and here is further illustrations has been shown here. Now when from the upper sides a downward vertical direction some force is applied or the acceleration is applied, so then what will happen, the springs will be bent towards downwards, right? Now if you look at this, this is the spring June version of the spring, so then what will happen, the spring end which is towards the frame region, so there the resistance will increase because that will experience the tensile force, whereas the portion of the beam which is towards the mass region, in that portions it will experience the compressive force, and that's why the resistance will decrease. So the resistance which are towards the frame sides, total 4 resistors are there towards the frame side, those will show increase in resistance when some vertical direction force is applied, whereas the other force which are towards the mass region, they will experience that decrease in resistance when some downwards vertical force is applied. Right now, obviously, if some upper side force is applied, then the other things will happen. Fine. So here again, just for further illustrations, here we have shown that the piezoresistors which are towards the frame sides, those will show that upper arrow means increase in resistance. So here the frame sides, it will give you the increase in resistance, whereas the piezoresistors which are placed towards the mass sides, they will show you the decrease in the resistance. Right now, suppose R1, R2, R3, R4, likewise, if we give the name, accordingly we have connected in the Wheatstone bridge configuration. So like in this case, Rm correspond to the piezoresistors which are towards the mass side, and Rf correspond to the piezoresistors which are towards the frame side. Fine. So basically, towards the mass side we have total 4 piezoresistors, and towards the mass sides they will show you the decrease in resistance. So that's why 2 mass sides will be in this side, this arm, whereas another 2 mass sides will be in this diagonal arm. So they will show you the decrease in resistance, whereas the frame side RF, here we will put 2 frame side resistors or the piezoresistors, and in its diagonal we will put another 2 frame side piezoresistors, and this will be the Wheatstone bridge configuration. Right. So as we said that what we have illustrated, that when the device undergoes an acceleration, the proof mass moves up or down, causing 4 of the resistors to increase and another 4 of the resistance to decrease their value. Right, and this results in an output voltage change proportional to the applied acceleration. Now these 8 resistors has to be connected in this particular fashion so that we can get the maximum output. Right, and here one point is mentioned, and so as to achieve minimum off-axis sensitivity. So what do we mean with off-axis sensitivity? So there are basically 2 types of sensitivity. One is the main or primary sensitivity. Suppose in this case, from the vertical side we are applying the acceleration or the force. So that typically we consider as the z-axis. Right. So z-axis is my target. Right. So z-axis is my primary axis, or that we call as the sensing axis. Now, if I want to design an accelerometer which should be sensible to z-axis only, then my requirement should be so that if from some x-axis or y-axis, if some undesired acceleration or force is applied, then that should not affect my performance. Right? But if it is affected by undesired x and y axis as well, then we can call that there is some cross axis or off axis sensitivity also there. So obviously what should be our requirement? Then that the sensing axis sensitivity should be maximum, right? And the off axis or the cross axis sensitivity, they should be as minimum as possible, so that some undesired directional force or accelerations cannot affect my measurement. Right? Got it? Is it okay? Or any doubts? Yeah. So please feel free to ask if you have any doubts. Okay. Now, as you told that for z-axis acceleration, all frame end resistance will increase while all mass end resistors will decrease. Hence, for maximum normal acceleration to the the bridge must be configured in this particular configuration, so that if we connect it in this particular configuration, then the primary or the sensing axis sensitivity will be increased, whereas that cross axis will be decreased. Fine. So this is the Wheatstone bridge configuration for the piezoresistive type accelerometer, which will give you the voltage output, and that voltage output will be the function of the applied input acceleration. And by measuring the output voltage of the bridge, we can measure the accelerations which is unknown. Fine. Is it okay? The basic working principle of the piezoresistive accelerometer along with its Wheatstone bridge configuration. Fine. Yeah. So let us go to the next slide. So here in this slides, just some representative results we have shown. Fine. So here, just for example, at ADE Bangalore, they have one red table or the test setup which can be used for this accelerometer testing, right? So accelerometer testing means, so here on this table we will be mounting our that piezoresistive accelerometer device, and then when the accelerations will be applied, because of the accelerations the resistance change will happen, and we will use some circuit board also which will convert the resistance change into voltage, and that circuit output, so this is the circuit, and that circuit output we can measure with the help of some either oscilloscope or some multimeters like this. Fine. So just for representative purpose, suppose for in this case z-axis is my primary requirement. So here we have just shown the results for all z-axis, x-axis as well as y-axis. So obviously that this is the z-axis response, that is my main requirement, and x-axis should be, so x-axis means for from the graph aspects, right? So along this axis we have the acceleration, and along this axis we have the output voltage, and if we plot it, so then from there we can from this response we can understand that how much linear the device characteristic is, or what will be the sensitivity, right? So those are the things we can see. And in this lower table we have shown the corresponding data as well. So here what we can see in z-axis, that is our primary requirement, the sensitivity is 0.6 millivolt per G, and nonlinearity is only 0.2%, right, for this particular car. Whereas if we look at the x and y axis, although they looks like some linear response, but look at the unit. So in our primary sensing axis it is 0.6 millivolt per G, whereas for x-axis and y-axis the sensitivity is, you look at the unit, 3 microvolt per G, here also some 3.2 microvolt per G, right? So what do we mean by that? That means if some undesired acceleration also is applied along x and y axis, then the device will not be affected much, because you see this main sensitivity is 0.6 millivolt, whereas the other cross axis are only 3 microvolt. Fine. So that is more than 100 times, right? Yeah. So that means that is the actual sensitivity. So this is just to give you the idea that what are the different features or different parameters we have to look into when we will design a particular sensors, and then after doing the design, finally we have to do that before fabrications we have to do some simulation analysis, and there we have to see that whether we are achieving our target or not. Once we are satisfied with our design, analysis and simulation, then only we can go for the fabrication. Once the fabrication process is done, then we have to do the testing, the packaging, then bonding, packaging as well as the testing, and after testing we have to satisfy ourselves that whether we are achieving our target parameter values or not, right? So here just to point out, here one point is mentioned that structure with gold and without gold. Here also with gold, without gold, here some with gold is there. So just you know that with gold, some that means the piezoresistive accelerometer design what we have shown, that one main proof mass and 4 springs. So sometimes on the proof mass we have to deposit some small amount of gold, and this gold depositions, the requirement is that if you deposit the gold, so then it will increase your that sensing axis sensitivity, and it can reduce your off axis or cross axis sensitivity. So that is mainly because of the gold that you can reduce your undesired sensitivity, that undesired cross axis sensitivity, right? So this is just the some representative results has been shown here. Okay. Now if we formally see that for this piezoresistive type accelerometer, what are their advantages, what are their disadvantages? So it is similar to our piezoresistive type pressure sensor, where what we have seen that whenever we have some resistive type measurement, so then the advantage is it is quite simple, as we have listed over here. Simplicity, fabrication process is also simple, and since the resistance change is there, so it will not be affected by some parasitic capacitance or electromagnetic interference. So these are the advantages. But when we will look into the disadvantage, so then similar to the piezoresistive pressure sensor, the main disadvantage is the temperature sensitivity. And to compensate this temperature effect, we need some sort of temperature compensation circuits as well. And its overall sensitivity is also less than the capacitive type device. Fine. So these are the relative advantages and disadvantages of the piezoresistive accelerometer. Fine. So with this we have completed the piezoresistive type accelerometer. Is it okay? Is it making some sense or any doubts? Yeah. If you don't have any doubts, so then we will move forward to the next topic. Okay.